What we're going to have a look at now is forces in a spring. Going to do maybe three or four videos on this, so we'll just call this one number one. Now, I portray my spring unstretched like that. Then, if we were to let a particular mass hang off it, it would hang down to that length. So we can say at this point that mg equals kx. Very important to remember that. And we'll call that x, because that was how much it got stretched. Now, one of the points that we've made, and we've made it a few times, is that the gravitational potential energy that's lost here, mgx, okay, can't all be taken up by the spring. The spring can only take up half kx squared. So if we have a quick look at the energy let's have a look at the energy in the spring compared to the potential energy lost. So we call that energy elastic compared to energy potential gravitational. Then what we can say is that 1/2 kx squared over mgx, if we do the maths, obviously that 2 can come down here. We know from this first little bit here, mg equals kx, that k is equal to mg over x. So if k equals mg over x, and we make the substitution, mg over x times x squared, right? So mg x squared over x, and then we've got mgx on the bottom. We see some beautiful things happening. The x's cancel, the mg's cancel, and all we're left with is that 2 that we had up there. So we can say that always the energy, the elastic energy held at that point compared to the potential energy is 1/2. So getting back to forces though, what we will find is if we pull it down another x, or if we just let that other half of the potential energy that wasn't in the spring at the midpoint, what that means is it will actually still have some kinetic energy, and it will continue on. It will continue on until we get to a point where the full potential energy, which is now mg2x, equals 1/2 k, and when that will happen is when x again equals 2x squared. That's all going to work, right? If we make the substitutions, that all works. So we can actually show that x2x is where all the gravitational potential energy can be held by the spring. Now, that's because the whole energy goes up as a square, whereas the gravitational potential energy only goes up as the x, and not the square of the x. So, looking at the forces now, at this stage we've got mg equals x. At this stage, so if we drew that, drew the vectors, we'd have mg and kx. So the net force in the middle point is equal to 0. And that's why we say with this pendulum we've got, not pendulum, with this bouncy mass on a spring, we've got SHM. At that midpoint there is no net restoring force. Now at the bottom, at the top, what are the forces? Well, we've always got mg. We'll put the mg on the bottom one here too. We've always got the mg. But at the top, we've got no spring tension. Therefore, the only force acting on the mass when it's at the top is mg. And that's why the acceleration for a mass bouncing up and down on a spring can never be bigger than 9.8. At the bottom here, the tension has really built up. We've got a tension where we've got twice the displacement and therefore twice the force. So I'll just draw it off to the side. Our kx would be like that. So we've got a force upwards equal to kx, which is equal to mg. So we've got a net force up of mg at the bottom. At the top we've got a net force down of mg, and in the middle we haven't got anything. So the biggest amplitude you can have is this, when it's bouncing up and down with the full X. Of course, you can have little amplitudes up and down like this around the equilibrium position. Okay, snuff on that one.